In this video, we will build a Hypar model using NDN Tensile Membrane Software. This is a relatively simple model, but it will allow us to demonstrate many of the standard features in the software. Now let's start again and build the model. We'll first go into Setup, define our units, and our library locations. To input the geometry, we'll go into Edit, put it into a plan view, and simply start drawing in some nodes. I'll turn the labels on so you can see them a little bit better. I'm going to move two nodes up 1 meter and these nodes up 6 meters. Now I'll add some strut elements and add some work lines just to help me visualize what I'm doing. I'm going to insert a node right in the center and now generate membrane elements. No need to have the node labels on anymore. I'll mirror this into a full model. Mirror it again in the other direction. Delete the work line elements because we no longer need them. Trace cables around the perimeter. Project our tie cables down. And apply geodesics to the first side of our membrane elements. We now have the basic starting geometry defined. Let's get the model organized onto layers. We'll back out of Edit, go into Layer, and simply type in some layers. To put elements on layers, we simply click on the layer and assign it. Edge cables will assign to cables selected by string. Tie cables, assign cables selected individually. Fixed nodes, we'll assign individually to our fixed nodes. The next step will be to define our properties. We'll work on the nodes first and assign by layer the proper degree of freedom code. For the elements, we'll use some default properties. The default properties will define all of our material and section properties and also a pre-stress of 1.8 kilonewtons per meter. We'll apply the defaults. For the cable pre-stress, we'll take a guess at 10 kilonewtons in our tie-down cables, and we'll use the estimator for our edge cables. We'll define a length sag ratio of 14 and let the software figure out what the appropriate force is. We now should have all of our properties defined. We'll check by systematically going through these labels. And it looks like everything is properly defined. Now we are ready to do the form finding on the system. We'll go into Shape, Shape Generate, and simply click Go. We now have the shape that is in precise equilibrium with the pre-stress forces that we defined. We have a uniform, equal pre-stress of 1.8 kilonewtons per meter in all directions of the fabric. It's important to note that by using a defined equal stress field, we achieve the minimum energy, minimum surface area shape. This eliminates all stress concentrations, eliminates shear stress, and gives us the most structurally stable, appropriate system. The next step in the process is to define our loads. We'll go into the load environment and define some load cases. First load case will be pre-stress and dead load. For the second load case, we'll use a snow load of 1 kPa. For the third load case, we'll put on a uniform uplift of 0.7 kPa. Now let's get a little bit more interesting. We'll increase the wind load to 1 kPa blow the wind in this direction, and to take into account the aerodynamics, we'll pull wind coefficients out of a building code, in this case ASCE 705, and generate the coefficients. Make another load case, new wind direction, generate coefficients. Another load case, and this time use a different library file. One more load case. Alright, we now have 6 load cases defined. Let's do the analysis. We simply go into the Analyze environment, click on Analysis, and then Go. Looks like all load cases converged. Incidentally, NASA has tested this matrix solver and have concluded it's actually the fastest matrix solver in the world. After analysis, we go into the post-processor to look at our results. As an example, here are the deflections under the various load cases. Cable forces, fabric stresses, here we are under pre-stress and the other load cases. Reaction forces, text on, these are resultants. We can also look at the components. Another important thing that we do in the post-processor is member design. This allows us to automatically size our members based on the analysis that we just did. As an example, remember when we built the model, we assumed 12 millimeter wire rope for all of the cables. Now let's find out what size we really need. Based on the analysis, we need 14 millimeter wire rope in the edge cables and 9 millimeter wire rope in the tie downs. In the struts, we assumed 140 millimeter pipe. Now let's size the members. So based on the analysis, we really need 165 pipe. What the program did was select the lightest weight section that satisfies the analysis and meets this building code. We have our choice of several different building codes. So now we know what our member sizes need to be based on the analysis. These sizes are different than what we originally assumed. So we will update our model. So our model now contains these same sizes. And since the stiffnesses have changed, we'll rerun the analysis. And back into the post-processor for a final check. Everything checks out okay. Steel's okay, and the cables are okay. Now let's pattern our structure. We'll define a fabric width and seam styles down here. There's many ways to do patterning in NDN and several ways of doing the flattening. We can flatten either through geometry or through more advanced analytical minimum energy methods for more accuracy. Today we'll pattern using the automatic width method. We'll define a seam in the middle and tell the program which direction we want to pattern in. Now the software will iteratively work until it finds exactly where to put the seam so the pattern fits precisely on the fabric roll. The next step is to define our seam types. We'll assign lap seams to the centerline seam work lines and a pocket to our edge cables. Output will be in the form of DXF files. We can go into Setup and define in this area what information we would like put in the DXF files. Then we simply go into Output and write out the files. The files are suitable to read into AutoCAD or directly into the software for your wide area cutter. This is the DXF file that we just wrote out. Remember, while we were at NDN, we defined what information we wanted in this file. Here we can see the cut lines and the match lines, and notice that all edges of the pattern are splined.